Hello guys, I am Rudra Tiwari. I, along with my team members, presenting the network analysis tool called the Networkit. In my team members are Kisan Tamboli, Ranjan Mandal, me, and Manish Kumar Saw. In my presentation, I will cover the introduction, Networkit main goals and modules, installation process, creating the graphs by using the APIs, analysis, demonstration, and conclusion. First, I am taking the introduction. We have used many network analysis tool, and all of them have covered all those topics who have covered in the classes till date. Networkit has some special feature. One is it is the open source toolkit, and second it is working on the large scale network analysis. Large scale networks have the size range from the thousands to billion of the edges. Networkit, if we compare with the other network analysis tools like a Network X, albeit it focuses on the parallelism and scalability. Basically, it is the Python module, but it has the its performance is high just because of the it implements all the algorithm in the C++ and expose the APIs in the Python via the Python toolchain. Networkit is maintained by the research group modeling and analysis of the complex system of the Institute of the Computer Science at the University of the Berlin. As I already explained, it is using the C++ at the backend for the high performance, and for the parallelism it is implemented the OpenMP, that is open multiprocessing, and expose the API in Python to make the program easy. It also integrate some external tools like Jupyter Notebooks, Gephi, SciPy, Matplotlib, etc. It has the multiple modules that covers the in a computation on the network analysis, but we are taking some few uh, modules: community, community detection, centrality measures, graph generators, distance computation, link prediction, sparsification, dynamic algorithm, basic graph, how to create the basic graphs, and algebraic algorithm. Before using the network kit, we must have all the requirements, prerequisites to have the environment of the network kit. So in the prerequisites, we must have the C++ compiler like G++ 7 version 7 or higher, C lang plus version 5 or higher, OpenMP for parallelism, Python 3, make, and Python version 0.29 or higher. How to install in the Linux? Just what we have the common commands to install the any package. We use the apt install build essential in the Ubuntu. It install the compilation tools. For the installation of the Python 3 and pip3, we can use the command install python 3 dev, python 3 pip. To install the CMake and Python, use the pip3, install CMake Python, and finally install the network kit that by the using the command pip3. For more detail about the installation, we can use the link that is given in the bottom of the this slide. That is the github.com/networkkit/networkkit. Networkit 9.0 also support for the Windows installation. So for how to install the Windows, we can use the pip3 command and install the Python, and finally we install the Networkit. This is the main architecture uh, based on the Networkit is working. In bottom you can see it implement the C++ and OpenMP algorithm to implement the algorithm, and top of it it gives the wrapper classes in Python, and on the top of this it gives the API in the Python that uses the Python wrapper classes. You can see in this picture it can use the different data set from the sci-fi, NumPy, Pandas. These are the data analysis tools, Matplotlib, etc. And it also work on the NetworkX. That is another network analysis tool. Here there are the multiple use cases. So we will take how to read a graph, how to draw a graph, how to visualize a graph using the NetworkX, computation of the central vertices, graph generators, community detection, and centrality measurement, etc. Networkit graph creation. How to create a basic graph by using the Networkit. First, import the Networkit. Here you can see the one piece of the program. It import the Networkit as NK, and call the graph. It using the graph class to create the graph instance nk.graph. It takes the number of the nodes as an argument. Here we have passed 5, so it will give the instance of the a graph with the nodes 5, and further we can add edges in between the vertices what we have passed by calling the method add edge in the graph instance. So here we have added 6 edges between the vertices, and then we call the overview function. Overview function will give the all the properties of the graph what we have created in the graph. So in right side you can see the network properties what we have created. It shows the nodes and edges that are the 5 and 6, directed or not directed. It is the boolean value. Here we have created the undirected graph and unweighted graph. That's why it is giving the false. If there is any isolated nodes, then it gives the number of the isolated nodes. Here is the 0. If any self loops exist in the network, then it gives the self loop number of the self loops. Here it is 0. It gives the density, that is the 60% here. Clustering coefficient, here the 0.53. Minimum maximum average degree, here it is showing 1, 3 and 2.4. Number of connected components, how many number of the connected components in the network. Connected components means if any network is divided into multiple components, means sub networks, then it gives the component, then it is called the component. So By calling the overview method, it is giving the number of the connected component. Here is only one component is there. All are the nodes are connected to each other. No sub network is there, so it is showing the 1. And size of the largest component, it gives the number of the nodes in the largest component, that is the 5. There are the too many methods for the creating of the graph and analysis of the different properties. I am taking one by one. One is the add node. By calling the add node, it will add a node in the network in the sequence of the previous one. Add nodes, by calling the add nodes method, it will add in the multiple nodes in the network. Added method will add the edges between the two vertex what we are passing in the argument u and v. Remove node. Remove node will remove the nodes that is passed in the arguments. So here it is remove the node number 2. Hash node will give the existence of the node. If it is there, then it returns the true. It is the boolean value. Boolean value. It returns the boolean value. Restore node. If we have removed any node, then we can restore further by calling the restore node. It will restore the node as well as the edges. Number of nodes. Number of nodes will give the number of the nodes present in the network. Remove edge. It will remove the edge as self-explanatory. Hedge edge. Hedge edge will give the presence of the if any edge is available in the network between the two vertex. Overview G. Overview of the graph. It will give the property of the graph. I have already explained. Weight. Weight will give the weight between the two vertices. It will give the weight of a edge between the two vertex. Is directed, is weighted, it will give the return. It will give the true or false if it is directed or not, if it is weighted or not, on the basis of that. Total edge weight. Total edge weight returns the weights of total weight of the all edges. Remove self loops. If any self loop exists in the network, then it remove all the self loops. We can iterate edges by calling the iter edges method, and similarly we can iterate the nodes by calling the iter nodes. We can also calculate the degree of any node, either it is in directed graph or undirected graph, by calling the degree method, degree in method, degree out method. Here we are taking what piece of the code for the undirected graph. We have created a graph with the number of nodes 5, and we add the multiple edges here. Here we are trying to show how to draw a graph by using the different network analysis tool. So here Networkit is providing an adapter called the NX adapter, and this adapter will convert the Networkit created graph in the Network X graph. So it is calling the nk dot nx adapter dot nk to nx, and graph we have created by using the Networkit as argument. Then it will return the Network X instance of the graph. And finally we call the draw method. You can see in the right side it is showing the graph what we have created. We have already explained the method iter nodes iter edges. Here the one sample program. uh, we are using the for loop and iterate the nodes, and all the nodes are printed by the calling the print method. One condition we have applied, that is the u is greater, if u is greater than 4, then print ellipsis. So you can see in the right side result is there. It prints 0, 1, 2, 3, 4, 5, and after 5 it will print ellipsis to alternatively. Similarly, it iterate the edges by calling the iter edges method, and it print all the edges. On the given condition, it will print ellipses also along with the other edges. Till now, we have talked about the introduction of the network kit, how to the create graphs, its APIs, and what are the properties of the graph we have created till now. Now we will see the implementation of the graph using the network kit by using the Jupyter notebook. So here you can see the Jupyter notebook. We are using the Google Colab. First we install the network kit by using the pip3 command. Since it is already installed, so it is showing the requirement already satisfied. Now we import network kit as NK. So it has been imported. Now we try to create the graph with the number of the node 5, and the graph will be directed. So we will pass the directed equal to true as the second argument in the graph class. It returns the directed graph instance and try to print the number of the nodes, number of the edges, and weighted and directed properties. So you can see the number of the nodes 5, number of the edges 0. Since we did not add any edge, so it is showing the 0, and weighted is false and directed is true. Now we are trying to add multiple edges. It is true. We can add more nodes by calling the add node method. And now number of the nodes is 6. We can add more edges by calling the add edge method. And now we would like to print the properties of the graphs by calling the overview method. So you can see the all the properties of the graph what we have created till now. You can see the degree sensitivity, minimum, maximum, average degree, density, self loop, size of the largest component, etc. Now we are trying to import the network X to draw the network kit graph. So I have already explained the it give the adapter to integrate with the other analysis tool like the network X. So we are using the network X to draw the graphs created by the network kit. So it gives the NX adapter method for calling the network X, and it converts the network kit graph to network X instance. And now trying to draw. So you can see the graph, it is directed, and number of the nodes beginning from the 0 to 5, 0 to 6, and all are the connected. It is the directed graph. We can remove the node by calling the remove node method and can see its presence. So it returns false. Again, further, if we require, then we can restore the same node By calling the restore node, it returns true. And now we draw the same graph again. So it is showing the two in the isolation because to restore again. So node is restored, but edges are not restored. This is again add more nodes, add more edge, and we can print the number of the edges and number of the nodes. We can also remove the edges by calling the remove edge method. We can iterate the nodes and iterate the edges. We have already uh, take this example in our presentation. So you can here you can see the result of by execute this piece of the code. It is also showing the edges names, and after satisfying the condition, it will also print the ellipses dot dot dot. We can convert the graph to the weighted graph by calling the graph tool class uh, a two weighted method in the graph tools class, and it converts the weighted graph of the instance of the weighted graph. And further, we can set the weight on the different edges, and now we are trying to print. So it prints the edges names along with their weight. You can see 1 to 3 edge has the 3 weight. Here I am done. Thank you.
So next topic is a centrality measure. So based on centrality measure, we assign some value or some rank to nodes. So common centrality measures are degree centrality, closeness centrality, betweenness centrality, and eigenvector centrality. Degree centrality. It was proposed by Nieminen in 1974. Degree centrality measures how many edges a node has. This centrality is based on the idea that the important node must have the most active and have large number of links with other nodes. Degree centrality is used to find influential people, highly visible actors, and highly exposed nodes. Closeness centrality. Closeness centrality indicates how close a node is to all other nodes in the network. It is calculated as inverse of the average of the shortest path length from the node to every other node in the network. Often used in social networks to know how fast the data propagates through short routes. Betweenness centrality is a way of detecting the amount of influences a node has over the flow of information in a graph. It is often used to find nodes that serve as a bridge from the one part of the graph to the another. Eigenvalue centrality. Eigenvalue centrality is the algorithm that measures the transitive influence of the nodes. A high eigenvector score means that a node is connected to many nodes who themselves have high scores. The PageRank algorithm is a variant of the eigenvector centrality. For example, suppose we have a website and we got link from several different websites. If the linked website having domain score is low, then our website domain score will be low. But if the linked website domain score is high, then our website score will be high. So to calculate centrality, there is a module centrality inside there. different classes are available. For getting degree centrality, we call nk.centrality.degree centrality and we pass the graph, then call the run method, then we call the ranking method. So ranking produced top 10 ranking of the degree in decreasing order. Similar for closeness, nk dot centrality dot closeness, then we pass the graph, and here we are calling generalized method of the closeness, then closeness dot run, and then call the ranking. Similar for betweenness, nk dot centrality dot betweenness class, we have to pass the graph, then call the run method, then call the ranking, and same for eigenvector centrality. The local clustering coefficient of a vertex in a graph quantifies how close its neighbors are to be being a click. Generating this centrality, we have generated a Gauss-Renyi graph, and we have generated graph with 30 nodes and 135 vertex. This one is the graph. So for degree centrality, we are counting nk dot centrality dot degree centrality and passing this graph, then degree dot run, then degree dot ranking. So it is giving top 10 degree centrality, node 13 having the highest degree, 3 having the second degree, third is having the equal degree to 3 1, third one ranking, 28 is having the degree 12, 29 is having the degree 12, 6 is having the degree 11. So we are getting 10 nodes. Second is a closeness centrality. For closeness centrality, we are same calling nk dot centrality dot closeness, and this is the generalized method of the closeness, then close dot run, then top 10 ranking of the closeness centrality. Similar for betweenness centrality, we are calling centrality dot betweenness and passing the graph, then betweenness dot run. So it is printing the ranking of the top 10 betweenness centrality. This is eigenvector centrality, so calling nk dot centrality dot eigenvector centrality, then run, then ranking. So it will also producing the top 10 eigenvector centrality.
Hi, my name is Ranjan Mondal, and this is the first part of my presentation. So, in this, I'm going to talk about Networkit distance tutorial, all pair shortest path, breadth first search, Dijkstra's algorithm, diameter, and eccentricity. All pair shortest path algorithms computes all pairwise shortest path distances in a given graph. It is implemented running the Dijkstra's algorithm from each node or the breadth first search if the graph is unweighted. So this is the piece of code in Networkit for it. So ngate.distance.apsp graph one. So graph one is the graph, and we this function returns the variable in the object apsp, and then we have to call this method run using the object apsp, and this the print function gives the apsp dot get distance. Breadth first search is an algorithm for traversing a graph which starts from the source node u and explores all the u's neighbors nodes at the present depth before moving on to the nodes at the next depth level. VFS finds the shortest path from a source to all the reachable nodes of an unweighted graph. So this is a piece of code for it, nk.distance.bfs, which takes all these parameters and returns the value in this bfs. Then we call this method run using the bfs.run. So this function bfs.distance, this bfs calls this method distance, which takes the target and gives the distance and prints the distance from the source to the target node. The number of shortest paths between the source node, bfs dot number of paths. Bfs calls this number of paths function, which takes the target and prints it. It returns the shortest path from the source to target. So bfs dot get path target prints this. Dijkstra's algorithm finds the shortest path from a source node to a target node. This algorithm creates a tree of shortest paths from the source to all the other nodes in the graph. Dijkstra's algorithm finds the shortest path from a source to all the reachable nodes of a weighted graph. So the for example, if you want to extract the largest connected component, we have to call this function nk.components.connected components.extract largest connected components. Pass this graph G and true, and have and this piece of code gives returns the value in the object new graph. Then you have to call this new graph method number of nodes using the new graph dot number of methods. So Networkit also has this facility of finding the diameter of the graph. This algorithm gives an estimation of the diameter of the given graph. In the second part of the tutorial, I'll show the computation of radius, diameter, and eccentricity. That will come later. And okay, the input graph must be connected, otherwise the resulting diameter will be infinite. So this is a piece of code for this. So new graph to a number of nodes gives you that. And we initialize the algorithm nk.distance, and we call this method diameter using the new graph, and algo is equal to 1. That returns the value in diameter, and we call this method run diameter.run. And to get the diameter, you have to call the method get diameter using diameter diam.get diameter. Eccentricity, the eccentricity of node U is defined as the distance to the farthest node from the node U. In other words, it's the longest shortest path starting from node U. So this is the piece of code for it: nk.distance.eccentricity.get value G comma source. So this completes the first part of my presentation, and I'll go next to the second part of my presentation. Hi, my name is Ranjan Model. This is the second part of my network science tutorial presentation. So we'll continue with with my network science presentation. So the eccentricity mu I of a node Vi is defined as maximum of Vj belongs to capital V minus Vi Dij. Dij is the distance between the node I and J, and we don't take into account the node Vi for the computation of the eccentricity of node Vi. So if mu I denotes the eccentricity of the node Vi, then every other node is within a distance of at most mu I from Vi. If the eccentricity of the node X is less than that of Y, then X is more central than Y. So first example, we take the very simplest example as I showed in the presentation. So there is a linear chain of four nodes V1, V2, V3, and V4. And if you want to compute the eccentricity of node V1, so its maximum of Vj belongs to capital V minus Vi Dij, that's equal to max of 1, 2, 3. So the distance, so it comes out to be 3. So the distance between V1 to V2 is 1, V1 to V3 is 2, and V1 to V4 is 3. So the maximum 1, 2, 3 is 3. And similarly, the eccentricities of the node V2 is equal to, comes out to be 2. Eccentricity of node V3 is equal to 2, and V4 is equal to 3. If you take the example to the below graph, as you can see in the slide, V1 is at the top, and V2, V3, V4, and V4, V5 are down. Then V1 is equal to 1 for every other node. Eccentricity is equal to 2. Eccentricity, what are the additional features? A node V of a graph which has the smallest eccentricity among all the nodes is called the center of the graph. This is very important when we compute the centrality measures. The center of the graph is the graph that I showed: V1, V2, V3, V4, V5 is equal to 1. The eccentricity of V1 is equal to 1. Our graph may have two or more centers. As you can see in the below graph, which has n number of nodes, and the vertices marked as V and W are centers of the graph. Their eccentricities are 1. If G is a clique on n nodes, then every node of G is a center. The smallest eccentricity value among all the nodes is called the radius of the graph. Radius is equal to eccentricity of a center. So in this graph, radius equal to 1, since V1 is the center and eccentricity of V1 is equal to 1. The largest eccentricity value is called the diameter of the graph. So we had seen all this in the first part of the presentation, but this is just an illustration to make things more concrete. how the eccentricity values are computed, how the radius is computed, how the diameters are computed, and what is the relation with the center of the graph, and what can be the centers of the graph. Okay, so consider the following undirected graph. We take a more complex example which has A, B, C, D, E, F, G, and H. For this graph, as you can see in the slides, we compute the closeness, centrality, and eccentricity. So if you see the below table, the closeness centralities are computed, and eccentricity values of A, B, C, D, E, F, G, H are respectively 3, 2, 2, 3, 3, 2, 3, 3, as you can see in the table. From the last table, the lowest eccentricity value is 2. In other words, the radius of the graph is equal to 2. Nodes B, C, F all have the eccentricity values equal to 2. Thus, the graph has three centers, namely B, C, and F. Next, I go to the network kit and show you the functionalities of network kit, the various methods that are available in the network kit tool for graph computations, and we'll go through some of them. There are lots of them, and we'll go only some of them. So, network kit is an open source toolkit for high performance network analysis. It's aimed to provide tools for the analysis of large networks in the size range from thousands to billions of edges. For this purpose, Networkit implements efficient graph algorithms, many of them parallel to utilize multi-core architectures. They are meant to compute standard measures of network analysis such as degree sequences, clustering coefficients, and centrality. Networkit is comparable to packages such as NetworkS, albeit with a focus on parallelism and scalability. So there are many things, and I'll straight away jump to how do you read and writing graphs in networkit. Let's start by reading a network from a file on the disk, and the file is a pgp giant compo.graph. It's an enormous file, it's a big file. As you see, the number of nodes and edges will tell you. So in this tutorial, we'll work on the PGP giant compograph, a social network, a wave of trust in which nodes are PGP keys and each represents a signature from one key to another. It is distributed with the network kit as a good starting point. There is a convenient function in the top namespace which tries to guess the input format and selects the appropriate reader. So you can see in the slide. So a read graph is a function that takes as input the file pgp giant compo.graph, and the format is metis, and we pass it this in a variable called g. So there is large variety of formats for storing graphs, data in files. For NetworkKit, the currently best supported format is the metis adjacency format. So next we go to the graph object. As you can see, the graph is a central class of NetworkKit. An object of this type, graph, represents an undirected, optionally weighted network. We will inspect several of the methods which the class graph provides, just several, not the entire exhaustive list. There are so many of them. Okay, so if we want to know the number of nodes in the graph, so we have to call this method number of nodes, and we have this g as our object. So g dot number of nodes is gives you the number of nodes in the graph. That's equal to, let's say, is equal to n. Similarly, number of edges can be computed using the calling the method number of edges, or g dot number of edges we store it m, and the print function we call n comma m, and if prints, if you see, the number of nodes becomes 10,680 and number of edges become 24,316, right? So there are other functions like g dot nodes. If you call this function, store it a variable and print v colon 10, as you can see below in the slides, that prints the top 10 nodes in the graph. G dot ages gives you the value and store it in the object e, and print e colon 10, that gives you the 10 ages. As you can see in the slide, 42.11, 42,11 is one of the age, 101,28 is one of the age, 111,92, and so on are these are ages. So these are the various functions, methods that are in the network kit to find the various features of the graph. Next, you want to check whether an edge exists between a pair of nodes. So we call this method has edge, passing the parameters the nodes, and g dot has edge returns whether true excuse me, true or false. As we have seen in the last slide, that there does exist an age between the node 42 and 11. The network is unweighted, meaning that each edge has a default weight of 1. So g dot weight, if you call this function, then it gives you the value as 1. So there are functions to check whether the graph is connected or not. So for that, so connected components, a connected component set of nodes in which each pair of nodes is connected by a path. The following function determines the connected components of the graph. So you call this function components.connected components, pass the graph G and store in the variable CC. Then you call the method cc.run, and then you call the method print number of components, cc.number of components. Okay, so it gives the number of components is equal to 1. Next, if you see the bottom of the slide, degree distribution, right? So it's very important. Node degree, that is the number of edges connected to a node, is one of the most studied properties of networks. Types of networks are often characterized in terms of their distribution of node degrees. We often visualize the degree distribution of, for example, network as follows. So you can have various such plots as scales, x axis, y axis, and all these things. And you can see the graph. Yeah. So you can see in the y axis we have the number of nodes, and x axis we have the degree. Okay, so you can have so many plots, and you can visualize such graphs in this network kit. So next we go to the uh, search and shortest paths. In the first part of the tutorial, I have taken up those BF. I have taken up breadth first search, Dijkstra's algorithm. So this is the piece of code for it. So if with this graph, you call it graph.bfs method. BFS method takes the graph G and the vertex V from which you want to start the BFS and returns the value in BFS. Then you call the method BFS.run, and BFS.get distance gives you the get distances and stored in the variable BFS.distance, BFS distance. The return value is a list of distances from the node V to the other nodes indexed by node ID. For example, you can now calculate the mean distance from the starting node to all the other nodes. So how it is done? You have this function sum. You pass this variable object where we have got the distances, BFS distance, and you divide by length of BFS distance, the number of BFS distances, and it turns out to be 11.3390. Similarly, Dijkstra's algorithm yields the shortest path distance from a starting node to all other nodes in the weighted graph. Because PGP giant compo is an unweighted graph, the result is the same as above. The BFS and Dijkstra gives pretty much exactly the same result, because PGP giant compo graph is an unweighted graph. So again, we have this piece of code, graph.dijkstra. Dijkstra, we have to call this method Dijkstra, passing the two parameters graph G and the vertex V, and storing the object Dijkstra. Then you call the method Dijkstra.run. Then we Dijkstra dot get distances method returns the value in sp dot distance, that is the shortest path distance variable, and it turns out pretty much the same. If you have the summation of all the distances by length of the shortest path distances, it turns out to be 11.3390, as you saw earlier for the BFS computation. So we can have lots of other features, example like community detection. This section demonstrates the community detection capabilities of Networkit. The community detection is concerned with identifying groups of nodes which are significantly more densely connected to each other than the rest of the network. Code for community detection is contained in the community module. The module provides a top level function to quickly perform community detection with a suitable algorithm and print some stats about the results. So we have this function detect communities that takes the graph as the input, and we have this piece of community.detect communities G, and if we type this, then PLM balanced comma PC detected communities in this number of seconds. And so the stats are this: number of communities, as you can see in the slide, is 105. Minimum community size is 4. Maximum community size is 654. Average community size is 101.714. And modularity is equal to 0.883963. So you can have this partition as well. The function prints some statistics and returns the partition objects representing the communities in the network as an assignment of node to community level. Okay, so you can have so many other things, and you can have the stats as it is shown in the below portion of the slide. Like average community size equal to 662, and average community size equal to 144. And this we can have other modularity as well, so which is a primary measure for the quality of the community decision algorithm. Okay, the value of modularity is in the range of minus 0.5 to 1, and usually depends on the performance of the algorithm and presence of distinctive community structures in the network. So this is a piece of code, right? So community.modularity, sorry, modularity.get quality communities, comma G. Then there is partition data structures and many other things. The result of community decision is the partition of the nodes set into disjoint subsets. It is represented by the partition data structure, which provides several methods for inspecting and manipulating a partition of the set of elements which need not be nodes of the graph. So you can see these things as it is written in the slides, this piece of code. And next, I go to, there are so many things. And yeah, next I go to the subgraphs. Networking supports the creation of subgraphs depending on an original graph and set of nodes. This might be useful in case you want to analyze certain communities of a graph. Let's say the community 2, a cluster of the previous results in the slides that you saw, is of further interest. So we want a new graph that consists of nodes and intra-cluster edges of the community 2. These nodes and edges of the community 2 form networkit.graph import subgraph and communities. Then you call this function communities.get members, and we pass this community to as a parameter and stored in the value c2, as you can see in the slide. Then you call this method subgraph and stored in the variable is g. So this variable object is g dot from nodes g comma c2 returns the value in this g2 variable, and communities are subset size map to number of, that gives you the number of nodes in community 2. And as you can see in the slides, is the result is 165. And if you print g2 dot number of nodes in the subgraph, that comes out to 165. As you can see, the number of nodes in a subgraph matches the number of nodes of community 2. The subgraph can be used like any other graph object, that is further community analysis, like as you can see, right, community dot detect communities g2, all these things. Then PLM balanced PC detected community is this, and you can have the stats like number of communities as 10, minimum community size 5, maximum community size 34, average community size 16.5, modularity is 0.742036. And then we go to centrality measures, and my colleague will take up the centrality measures. This ends the second part of my presentation. Thank you for listening.
Hello all. So as we see this Networkit is a powerful tool designed to facilitate network analysis and visualization, offering a comprehensive suite algorithm and functionalities. So one key aspect of network is its graph generator algorithm. So as we see in real life, graphs are used everywhere. When we are talking about road networks, when we are talking about transport networks, when we are about the friendship networks, citation networks, and everywhere. So sometimes it's very hard to get those data for the analysis part. So some algorithms are present. We can generate the graph look like a real world phenomena. So these algorithms are essential because allow researchers, practitioners to create networks models to closely resemble and structure found in various real life scenarios. So NetworkKit provides two algorithms for the many algorithms for graph generator. Basically, we are trying to see two algorithms. First one is the Ados-Renyi graph generator algorithm, and second one is the Barabasi-Albert generator. So Ados-Renyi graph generator says that it's create a random graph in the form of graph G. So n is a number. Here I am passing two parameters. First one is a n, second one is a p. So n is the total number of nodes I want to create in the model, and p is the total number of probability. So we can say that each edge included in the graph with probability p independently from every other edge. So how to generate this graph using the network kit? So network kit provides the direct function address any generator when so we have directly called this function with the parameters 20. I'm passing it 20 as the total number of node and 0.5 as a p-value. This is a probability of each edge it might be kept or not. So after the making instance, I just call it the generate. So it create the graph based on this algorithm, and after that I try to print the number of nodes and number of edges in this graph. So second one is a Barabasi graph, Albert graph generator. So Barabasi Albert graph generator says is initially connected network of N0 nodes, and new nodes are added to network one at a time. So Networkit provide direct function of Barabasi Albert generator. As I said that Networkit we can directly use those function and provide some parameters like 3 and 50. So here I am passing 50 for the total number of nodes I want in the graph, and 3. So 3 says that when I create a new node, when new node is created, then it connected to previously created 3 nodes randomly. Okay. Now after that we try to generate the graph, and also here I am trying to print the total number of nodes and total number of edges present in the graph. So one of key functionalities is Networkit graph plot is already available in this tool. So plotting is a very crucial part to analyze anything. When we are talking about the histogram plotting, blocks plotting, scatter plotting, and further things. So Networkit provides some plotting algorithm like cluster per degree plots, connected component size plotting, degree distributions, hop plot, and many others. So I'm mentioning here some few of the plotting algorithms, and clustering coefficient we are directly call this nk.plot.cluster per degree, and I pass it directly the graph file. So it creates the plot based on those parameters whatever we want, like cluster per degree, connected component size, degree distribution, or hop plot. So, as I said, that network analysis, it's very crucial for the how to generate the network. But sometimes we need to be a real network. So, real network in the market available in the many type of form. So, sometimes we get it from MTX format, TSV format, CSV format, and matrix market format. See, many another formats are available. So in this example, I'm taking a simple example how to create the graph based on the source vertices, array, edge vertices, and weights and etc. So you can use any kind of things like pandas, escapees, numpys, anything. So I am created here using numpy array. I am creating one array as a source vertices, and second array as a destination vertices, and third array as a weight of the edges. After that, I call the graph from Q. So I'm passing the parameter data, row and column. So it directly create the network kit graph for us. After that, we can apply any kind of methods provided by network kit. We can directly apply, we can analyze, we can modification, we can visualize anything we can do on this graph. So as I said, in the markets, many type of graphs is available. So you can find in this links. So first one is Amazon MIT Graph Challenge datasets. So you can go directly on this link, and you can find the many type of the graphs where you can use it for the visualization, where you can use for the analyze, you can compute something, you can delete something, add something, you can follow whatever you want to think. So there are Amazon dataset, uh, citation graphs, seek pattern graphs, email graph, social media graph like Finster, some Oregon's graphs, some protein to protein graphs, some road network graphs, and many type of graphs are available in this link. Same thing you can follow on the another things like uh, Stanford network dataset collection, network repository dataset, and many things. So when let's see how to use those graphs in our form. Suppose I want to take the graph on this data set and on of these websites, and how to create the graph and how to analyze those graphs things. So here I am making taking some example in the graph notebook part. So I am creating some basic example graph tool is KP form here. You can directly see the past. I can using the some additional manually additional graph, and I am taking some source and vertices, source and destination data set. After that, I data set age weight data. After I call this function graph from Q, and directly is create the graph for me. So after the for visualization, I am using the Networkx tool. So I am converting this graph to Networkx adapter, and the store is a variable NXG data, and direct I can draw using Networkx. So it's printing graphs like this. So here I am taking the 3 to 7 1 is, so 3 to 7 1 is, that's why it's created for 0 to 7 vertices, and remaining other vertices are isolated vertices. As I said, networking graph generator. So ADOS Rainy graph generator, as I said, I can pass the total number of nodes as a n and total number of probability of each edge as a p. So here I am passing the total number of nodes is 30 and total probability of each is 0.3. So after run it, it's printing the total number of edges, number of nodes is 30 and total number of edges is 139. So I can directly call it the overview. Overview is printing some properties of the networks, where is graph is directed or weighted, just like suppose graph is directed, then it's printed as a true, otherwise it's false, like weighted, same thing is the boolean function. And the total number of isolated nodes, and in this example here is 0, self loops in this example here is 0, density of the graph, clustering coefficient of the graph, minimum, maximum, average degree of the graph, and you can see the minimum degree of 3, maximum degree of 13, and average degree of 2.626, total number of connected components, and total size of the largest size of the connected components. So it can be print the basic properties of the graph. Also, we are trying to visualize this graph, whatever generated using the above generator algorithm. You can easily see this graph is printed. Now the second one, we are talking about the Barabasi Albert graph generator. So Barabasi Albert graph generator says I'm trying to be pass it as a Barabasi graph generator, and the total nodes I'm passing and 3. It means how many nodes are uh, connected when newly node are created. So here I am just printing the number of nodes, as I said that I passed in 50, so it's print as 50, and total number of edges is 144. So you can use EasyC to see the properties of the network generated by the Barabasi algorithm. So here you can see the minimum, maximum, and average degree. So minimum vertex degree is 3, maximum is 23, and average is a 5.76. And remaining same other properties are similar like as the previous one. So you can visualize the graphs generated by the Albert Barabasi algorithm. After that, I am trying to say that there are graph challenge data set, as I shown in the PPT. So how to take those graph in from the website, how to create the network kit graph, and how to analyze those graphs. So we directly get the graph using wget command. I directly download graph from the website, and I just create some numpy array based on this data, and after that I am using the function from graph from Q format. It's created the network kit graph for me. I'm making as a variable. Graph name is Oregon underscore graph, and I just try to print the properties of the graph. So here is printed the network properties, like node is total number of nodes are present in this graph 10671. Total number of edges present in this graph is 44004. As is directed or is weighted. So no, not this graph is not a directed and not is a weighted graph. self isolated nodes are present, so it shows this one vertex, total number of one vertices are present as a isolated nodes. And the self loop is zero, like minimum, maximum, average degree. So minimum degree is zero, as said that one isolated node are present. Maximum degree is 4624 and average degree is 8.24. So as the previous things, we try to get data from some Stanford University graph metadata set, graph data sets. I directly download the graph, and these graphs are in zip format, so I try to unzip first. After that, I just call it as a NK is a network kit that provided some snap reader graph reader format. So read graph is already available. You can directly read the graph based on the file format. So here file format I pass it the snap because I downloaded from snap dataset, and after that I try to overview the graph. Here as previous, you can see this is a 10670 nodes are present to 22002 edges are present and many more. So average degree and maximum degree, isolated vertices, everything is printed here. So degree distribution is there, and if you want to know about something plottings and all, so you can directly plot. I can plot the hop plot here. So hop plot type, whatever graph I created using the network read graph format. So I just try to plot the hop plots and many other things. So so this is from my side. Thank you so much.